Welcome to our presentation for Kick Back and Relax, learning to reconstruct the world by watching SlowTV. Monocular depth estimation is the task of reconstructing the 3D geometry of the world from a single 2D image projection. In the case of self-supervision, this relies on the photometric consistency across frames, where the predicted depth and motion are used to establish correspondences and reconstruct the target image. Self-supervised learning should be capable of scaling to much larger quantities of data, since no expensive ground truth is required. In practice, however, existing self-supervised approaches rely exclusively on automotive data such as Kitty. This limits generalization capabilities and results in poor performance in real-world scenes. Meanwhile, ironically, some supervised approaches train with much larger dataset collections. Unfortunately, many of these provide isolated image and depth pairs which are unsuitable for self-supervision. How can we address these limitations? We take inspiration from the concept of SlowTV, which consists of long videos with very smooth motion and few dynamic objects. We curate a total of 40 videos from worldwide locations and three main categories: nature, scenic driving, and underwater scuba diving. The final dataset has a total of 1.7 million frames, an order of magnitude larger than existing self-supervised datasets. We additionally propose a bag of tricks to further improve generalization, focusing on changes to the training recipe that don't affect the network complexity. Videos from the internet don't usually provide camera intrinsics. Instead, they're usually estimated using Colmap, which increases pre-processing and may be inaccurate. We take inspiration from Gordon et al. And predict the camera intrinsics using the pose estimation network. We showed that this improves performance compared to training using Colmap intrinsics. We also noticed that models can overfit to the training image size. For example, this model performs better when resizing back to the original aspect ratio, despite introducing distortions. We propose a simple aspect ratio augmentation to diversify the image shapes seen by the network. This augmentation samples center crops with varying sizes from 16 predefined aspect ratios. This includes both portrait and landscape, which gives our network additional robustness. Finally, we make some changes motivated by the handheld nature of our dataset. Existing methods force the pose network to always make a forward pose prediction. This makes sense in an automotive context where there is a strong prior on forward motion. However, handheld videos may exhibit more complex motion patterns. Handheld videos also have much smaller motion. This means there are more frames that overlap the target image. Randomizing the gap between the support frames diversifies the training motion. Our model was trained on a combination of SlowTV, Kitty, and Mannequin Challenge, and is publicly available on GitHub. We compare our approach with the updated self-supervised baselines from the monodepth benchmark. We also compare against state-of-the-art supervised approaches which use costly transformer backbones. We evaluate all models on a mixture of 9 outdoor and indoor datasets. Most of these results are zero shot, meaning that the model isn't fine-tuned and instead must generalize to previously unseen datasets. Our approach outperforms all other self-supervised models by a large margin and is on par with supervised methods that rely on LiDAR, RGBD, or structure from motion. Even in a driving domain similar to Kitty, our model outperforms the self-supervised baselines. However, our model generalizes better to different scene types, especially in an indoor setting. We evaluate our model in a real-world downstream task, map-free relocalization. This benchmark aims to relocalize an image from a single reference frame, using feature correspondences combined with metric depth to resolve the scale ambiguity. Again, our models outperform all other self-supervised methods and are on par with supervised ones. Map-free relog represents a challenging benchmark with highly diverse scenes and portrait images. Our model is nonetheless capable of generalizing to it without needing to fine-tune. Despite being a significant improvement over previous self-supervised methods, our model still has some limitations. Since our model is purely monocular and doesn't use stereo pairs, it can be less robust to dynamic objects. Self-supervised methods are also more sensitive to texture copy artifacts. Finally, the biggest performance gap with respect to supervised models is in indoor settings. This is because we rely exclusively on the Mannequin Challenge dataset as a source of indoor data. There is also the question of how to evaluate highly reflective and transparent surfaces. To summarize, we presented the first self-supervised monocular depth model that performs on par with supervised ones. We achieved this by introducing a new large-scale SlowTV dataset and improving the training recipe with a bag of tricks. Our code and pre-trained models are already available on GitHub. Thank you for listening.